Part 2 of Lesson 6.2 is going to be focused on trig proof problems. Now, yesterday in class, I had you add these to your note card for trig identities. These are definitions for sine, cosine, tangent, cosecant, secant, and cotangent. There are 6 trig functions in terms of opposites, adjacents, and hypotenuses for a right triangle. Okay, so these are the definitions we'll use when we're using right triangle trigonometry. But if you look down here at the bottom, these are some identities we'll use on these trig proof problems. These are basically telling us that sine and cosecant are reciprocals, cosine and secant are reciprocals, and then tangent and cotangents are reciprocals. Should have those on your note card. Then I also had you write these. I call these the quotient identities. Tangent is equal to the sine divided by cosine, and cotangent is equal to the cosine divided by sine. And then I had you write the Pythagorean identities at the bottom. Now there's 3 separate Pythagorean identities, and these are always true. But what I'd like you to do on your note card is to also write some equivalent Pythagorean identities just manipulated. So for instance, the first one, sine squared plus cosine squared equals 1, I'd like you to write underneath that sine squared is equal to 1 minus cosine squared, as well as writing cosine squared equals 1 minus sine squared. It's the same identity as the initial. It's just isolating the sine squared or isolating the cosine squared. In the same way, for the second Pythagorean identity, 1 plus tangent squared equals secant squared, I'd like you to write that tangent squared equals secant squared minus 1. And then I'd also like you to write that 1 equals secant squared minus tangent squared. And then lastly, for the third Pythagorean identity, 1 plus cotangent squared equals cosecant squared, I'd like you to write down that the cotangent squared is equal to the cosecant squared minus 1, as well as 1 is equal to the cosecant squared minus the cotangent squared. So include those on your note card for your Pythagorean identities, because there'll be times when it'll be beneficial to see all of those. Next on your note card, I'd like you to add these guidelines for solving trig proof problems. The challenging part about solving these trig proof problems is that they're not done exactly the same way every time. So these guidelines will help you as far as your approach on these problems. So the first thing I always try to do is guideline number 1. I try to use a Pythagorean identity. Now sometimes I can and sometimes I can't, so that's why I wrote when possible. The second thing I'll try to do is try to change everything into sines and cosines. For instance, if I have a tangent, a lot of times I'll change a tangent into sine divided by cosine. Or if I have a cosecant, then I'll oftentimes change the cosecant into 1 over sine. So that's guideline number 2. Guideline number 3 is to get common denominators and combine like terms anytime you've got 2 fractions being added together or being subtracted. And then guideline number 4 is to do some factoring. So sometimes you can factor and sometimes you can't. Oftentimes when you can factor, it allows you to simplify the trig expression. So these are your guidelines we're going to try to follow. Let's do a few examples. All right, the first one here, we're going to be using the Pythagorean identities to rewrite this expression. And the first one says tangent squared of 4 beta minus secant squared of 4 beta. Now don't get confused by the 4 beta. That's simply the same on both trig functions. So think of it as just a variable. But what we can do is we can look at our trig identity, and since so let's just switch the order of these 2 terms around. Let's write it as negative secant squared of 4 beta plus the tangent squared of 4 beta. Now what I'm going to do is I'm going to factor a negative 1 out. It leaves me with secant squared of 4 beta minus the tangent squared of 4 beta. And I like the way this looks right here, because if we go back to our note card, check this out right here. Secant squared minus tangent squared is equal to 1. So because of that, I can substitute a 1 in for this. So this becomes -1 times +1, which obviously just gives us -1 for a simplified answer. Part B, here we've got 4 tangent squared of beta minus 4 secant squared of beta. So the first thing I'm going to do here is I'm going to, again, switch the order around on these. So it's -4 secant squared of beta plus 4 tangent squared of beta. Then I'm going to factor a -4 out, leaving me with secant squared minus tangent squared. And again, we can substitute in a +1 for the secant squared minus tangent squared. And thus we get an answer of -4. Okay, next one we got cosecant squared of 3 alpha minus cotangent squared of 3 alpha. So I like the way this looks, because if we go back to our note card, if you look at this right here, cosecant squared minus cotangent squared is equal to 1. So that means that we can change this whole thing into just a 1. All right, part B, first thing I'm going to do is take a 3 out of those. That would give me 3 times cosecant squared of alpha minus cotangent squared of alpha. And again, since we've got cosecant squared minus cotangent squared, that's just equal to 1. So we get 3 times 1, which is 3. Next problem, we got 5 sine squared of theta plus 5 cosine squared of theta. First thing I'm going to do is take a 5 out of both of those, and that leaves me with sine squared plus cosine squared. And I like the look of that because if we go back to the note card, if you look right here, sine squared plus cosine squared is equal to 1. Thus, we can change what's in the parentheses into a 1. This gives us 5 times 1, which is obviously just 5. Next problem, we got a 5 sine squared of theta over 4 plus 5 cosine squared of theta over 4. Well, again, I'm going to take a 5 out of both of these terms. And that leaves me with sine squared plus cosine squared, which we know is just equal to 1. So that gives us 5 times 1, which is just 5. So here's a little shifting gears a little bit. We're just going to try and take and simplify this expression. I call this a trig proof problem. A lot of other people call these just trig identity problems. But we're going to simplify this expression as much as we can. Now, if you look at that numerator, we have the sum of 2 cubes. And in case you forgot the sum of 2 cubes, you can factor the sum of 2 cubes into x plus y times x squared minus xy plus y squared. Okay, so using that concept, let's factor the top into the sine of theta plus the cosine of theta times sine squared of theta minus sine times cosine plus cosine squared. Now, how has that helped us? Well, you can see on the bottom we've got a sine of theta plus cosine of theta, and now I can cancel that denominator with this factor. So that leaves us with what's left over inside the parentheses. I'm going to rewrite that in a slightly different order. Sine squared plus cosine squared minus sine times cosine. And I really like this right here because I know that that's equal to 1. So if I substitute a 1 in for that, that leaves me with the simplified expression 1 minus sine times cosine, and that would be our result for this problem. Next problem, we've got 9 minus tangent squared on top of tangent squared minus 5 tangent plus 6. So we're using factoring skills on this. We're going to take the numerator and factor that into 3 minus the tangent of theta and 3 plus the tangent of theta, treating that as the difference of two squares. In case you forgot, the difference of two squares, it factors into what I call conjugates. Now the denominator can be factored like a normal quadratic. So I need two numbers that multiply to give you 6, add up to give you -5, so that'd be -2 and -3. So there's the factored form of the denominator. And I like the way this looks. Now one little slight thing here is this looks almost the same as this, but they are different. You can see that the expression on the top that's highlighted has a +3. The expression on the bottom has a -3. So let me rewrite that numerator. I'm going to pull a -1 out of that factor. So that would give us a -3 plus the tangent of theta. And the second factor stays the same. Denominator, I keep that the same. Tangent of theta -3 times tangent of theta -2. And now I can cancel the tangent of theta -3 on the top and the bottom. And so we're left with our expression. I'm going to distribute the -1 to get -3 minus the tangent of theta, all divided by tangent of theta -2. Okay, last problem. I'm trying to do some factoring here, but it doesn't look like we can do any factoring because we don't have any squares. So then what I'm going to try and do is I'm going to try to substitute in sines and cosines. Let's change that numerator into 2 minus sine of theta over cosine of theta. Let's change our denominator into 2 over sine minus 1 over cosine. Well, now what I want to do is I've got two terms in my numerator, I've got two terms in my denominator. I want to put them together. So putting them together is going to give me 2 cosine of theta over cosine of theta minus sine of theta over cosine of theta. I got a common denominator with those two terms. Same thing in my denominator. And let's see here, that'll be a sine squared. So now that I got common denominators, I can put them together, and we would get 2 cosine of theta minus the sine of theta divided by cosine of theta. That's my numerator. My denominator would be 2 cosine of theta minus sine of theta divided by sine of theta times cosine of theta. And now we can take the top times the reciprocal of the bottom. So if I take sine cosine divided by 2 cosine minus sine, that wipes this out. And now I'm liking the way this looks because I can cancel that cosine with this cosine. And then I can cancel 2 cosine minus sine with 2 cosine minus sine. So that leaves me with just sine of theta for a result. So this is a little introduction into some trig proof problems using our different identities to simplify the expressions. Hey, I ever tell you guys about my dad? Well, he used to be a teacher, but eventually he stopped because he found out he didn't have enough class. Good stuff.